When we talk about the physical property of an object, its existence is independent of observation. For example, an apple will be red even if we don't observe it. But according to quantum mechanics, an unobserved particle does not possess physical properties that exist independent of observation. Rather, such physical property arises as a consequence of measurements performed upon the system. Many physicists rejected this new view of nature. The most prominent objectors were Einstein, Podolsky, and Rosen. According to them, if we can, without disturbing a physical system, predict the value of physical quantity with certainty, then there exists an element of reality associated with the physical quantity. And asserting the physical process occurring at one place should have no immediate effect on the element of reality at another location, which results in certain locality of the process. So in 1964, John Bell derived an inequality for correlation measurements which showed that the results for entangled states which are predicted by quantum mechanics could not be reproduced by a local realistic theory suggested by EPR. And in 1969, CHSH, it stands for Clauser, Horn, Shimony, and Holt, presented a similar inequality which was experimentally tested. So first of all, let's check the local realistic theory supported by EPR for the interpretation of entanglement. Suppose Alice and Bob are living far apart and share a Bell state beta 11, where beta 11 is equal to 0 1 minus 1 0 by root 2, and by some arrangement they both receive a particle at the same time. On receiving the particle, Alice randomly decides to measure the property Q or R of the particle, and the measurement results for Q or R would be either plus or minus 1. Similarly, after receiving the particle, Bob randomly chooses to measure either S or T with outcomes plus or minus 1. Note that the timing of the experiment is arranged so that Alice and Bob do the measurement at the same time. Therefore, the measurement which Alice performs, that is for the property Q or R, cannot disturb the results of Bob's measurement, that is the properties S or T. Now we can define a measurement operator M equal to Qs plus Rs plus Rt minus Qt, which can be simplified as Q plus R into S plus R minus Q into T. Now since Q, R, S, T all can take the values of either plus or minus 1, this value would be equal to plus or minus 2, as you can check by yourself. Now let us define a probability distribution given by P such that the mean value of the quantity or the expectation value of the quantity M would be equal to summation QRST into the probability distribution into the quantity M. Now we know the value of M is 2 and the probability would always be lesser or equal to 1. Therefore, the expectation value or the mean value of the operator M would be lesser than equal to 2. Also, we can write EM, which is equal to expectation value of Qs plus Rs plus Rt minus Qt, which is equal to the sum of expectation value of Qs plus expectation value of Rs plus expectation value of Rt minus expectation value of Qt, and we know this value is lesser than equal to 2. Therefore, we can say that expectation value of Qs plus expectation value of Rs plus expectation value of Rt minus Qt is lesser than equal to 2. So this result is called Bell's inequality or CHSH inequality. Now we'll calculate the same expectation value of M with the help of quantum mechanics. Here we work with a Bell state beta 11, which is equal to 0 1 minus 1 0 by root 2, which Alice and Bob shares. We also define the observables Q equal to Z1, R equal to x1, and S equal to minus Z2 minus x2 by root 2, and T equal to Z2 minus x2 by root 2, where Z1 x1 are the operators in Alice's system and Z2 x2 are the operators in Bob's system, such that we know Z1 equal to Z2, which is our poly Z gate, which is equal to 1 0 0 minus 1, and x1 equal to x2, which is equal to poly x gate, which is 0 1 1 0. We can also define the operations on our qubit such that Z operating on 0 gives us 0, and z operating on 1 gives us -1. Similarly, x operating on 0 flips the bit to 1 and x operating on 1 gives you 0. So now let's calculate the expectation value of QS, RS, RT and QT with respect to state beta 11. So first of all, let's calculate the expectation value of QS, which can be also written as QS, which is equal to beta 11 QS into beta 11, which can be written as beta 11, and Q and S are actually the tensor products, that is Q tensor product S into beta 11. So putting the value of Q and S, we can write this as beta 11 into Q was equal to Z1, which is a poly Z gate, which is sigma Z tensor product. S was minus Z2 minus X2 by root 2, which is minus of sigma Z minus sigma X by root 2 into beta 11. So let's take the minus sign and root 2 common outside, which would be equal to minus of 1 by root 2 into rho of beta 11 sigma Z tensor product sigma Z into beta 11 plus beta 11 into sigma Z tensor product sigma X into beta 11. So let's open this ket, which would be 1 by root 2 beta 11 sigma Z tensor product sigma Z into 0 1 minus 1 0 by root 2 plus beta 11 sigma Z tensor product sigma X into 0 1 minus 1 0 by root 2, which would be equal to minus 1 by root 2 beta 11. Now we know these two qubits are the tensor product of zeros and 1. So we can write sigma Z tensor product sigma Z into 0 tensor product 1 for this ket minus sigma Z tensor product sigma Z into 1 tensor product 0. Similarly, we have beta 11 into sigma Z tensor product sigma X into 0 tensor product 1 minus sigma Z tensor product sigma X into 1 tensor product 0. Now we know A tensor product B into state A tensor product state B would be equal to A operating on A tensor product B operating on B. Using this expression, we can operate sigma z's and sigma x here, which would give us minus 1 by root 2 into beta 11. Sigma z operating on 0 gives us 0 and sigma z operating on 1 gives us minus 1. So similarly, sigma z operating on 1 gives us minus 1. This would be plus, and sigma z operating on 0 gives us 0 divided by root 2. So here also there would be root 2. Again, sigma z operating on 0 gives us 0 and sigma x operating on 1 gives us 0 minus sigma z operating on 1 gives us minus 1. This would be plus 1, and sigma x operating on 0 gives us 1 divided by root, which would equal to minus 1 by root 2. Now I can open beta 11, which would be 0 1 minus 1 0 divided by root 2 into minus of 0 1 plus 1 0 divided by root 2 plus 0 1 minus 1 0 divided by root 2 into 0 0 minus 1 1 plus 1 1 divided by root 2. Now we know the inner product of these two terms would be 0, since there is no common basis set here. So this term would be 0. So we'll only evaluate this term, which would be minus 1 by root 2. 0 1 into 0 1 would be minus of 0 1 0 1. 0 1 plus 1 0 would be 0 1 1 0. Minus of 1 0 0 1 would be plus of 1 0 0 1, and minus of 1 0 1 0 would be 1 0 1 0 divided by root 2 would be 2, which would equal to minus 1 by root 2. These terms would be 0 and these terms would give us 1. So minus 1 would be minus 2 by 2, which would be minus 1, and minus 1 would be 1. So the final answer would be 1 by root. Therefore the expectation value of QS would be 1 by root 2. So similarly, we can calculate the expectation value of RS, which would also be 1 by root 2, expectation value of RT, which would be 1 by root 2, and expectation value of QT, which would be minus 1 by root 2. So based on this, we can write the expectation values for this equation such that E of QS plus E of RS plus E of RT minus E of QT would be equal to 1 by root 2 plus 1 by root 2 plus 1 by root 2, and minus plus would be plus 1 by root 2, which would be 4 by root 2, which gives us 2 root 2. That means E of QS plus E of RS plus E of RT minus E of QT is equal to 2 root 2. But previously we got the value having an upper bound of 2. But quantum mechanically, we get 2 root 2. And additionally, there has been a huge experimental effort with the outcomes speaking in favor of the quantum mechanical result. So, the Bell inequality that was based on the assumption of the local realistic theory is wrong. But what did we learn from Bell's inequality? That it taught us that entanglement is a fundamentally new resource in the world that goes essentially beyond classical resources. And in the future, we should exploit this new resource.